Howdy ho there. Bienvenidos. Glad to see you again. Let's not beat around the bush this time. Let's just get right to it and look at a diagram of what we did last time and what we hope to do today. We're working on getting our signup handler fully functional so we can make real calls to it with an HTTP client like Postman or curl. We implemented the signup method in the user service along with create and find by ID in the user repository. We also added a Postgres service container at the root of our project inside of a Docker compose.yaml file. In order to get the handler working, we have two major steps remaining. The first is to create an implementation of the new pair from user method inside of a token service, which we've yet to create. We'll get going on that today. The second thing we need to do is to establish a connection to this created Postgres server from inside of our application and perform dependency injection, meaning Postgres gets injected into a user repository, gets injected into a user service, which is injected into the signup or the handler layer. We also need to make sure our token service is injected into our handler layer. Once we do that, we should be able to run Docker Compose up and get our reload server environment running, and we should be able to make calls to our signup handler and actually insert a user inside of the Postgres database. So let's get working on the token service. Let's open up the signup handler inside of the handler folder to remind ourselves of the call signature of the new pair from user method that we reach out to in the token service. So if we scroll down here, we see it highlighted. What this does is takes a user, which we've created in the user service signup method, and then reaches out to the token service to create a new pair of tokens. The third parameter here is an empty string, and this is used for passing the ID of the user's current refresh token so that it can be invalidated before providing a new refresh token. This is passed as an empty string for signing up a user, as the user won't yet have any token because they do not yet exist. We'll end up handling this token ID or this empty string in a couple of tutorials, but it's going to require setting up a Redis database and a token repository, which the token service can interact with. So let's hold off on that for now and get working on the implementation of the token service. So here inside of the service folder, let's right click or do it however you like and create a new file called token service or token_service.go. I'm starting to wonder if adding this underscore service is redundant, but it's too late. I've stuck with it. So I've added some code to this file and included the automatic imports. So let's look at the first thing that we do here, and that is to define the token service struct or the properties which our token service will depend on, or the fields. And we see here that we have some priv key or private key of type RSA private key and a public key of type RSA public key. We also have just a plain old string of a refresh secret. We then follow this sort of factory pattern that we did earlier, where we use a new token service method, or I guess function, factory function, to initialize an interface version of the token service, and then we return the concrete implementation. As a reminder, I already brought this up last time, but I've been making a mistake in creating these structs here as package public with a capital letter, like a capital T for token service. It might make more sense to define these with a lowercase t, as we don't want the user to be able to instantiate a service by calling this struct directly or by instantiating this struct. So we'll go ahead and make this update to our services and repositories probably in 2 tutorials. So now the question arises, what are these public and private keys that we see here? And then what is this refresh secret? Remember that I said we'll be using JSON Web Tokens or JWTs as our authorization mechanism. So let's do a little primer about what these are. I'm here at a website called jwt.io, which is made by auth0, I don't know how you say their name, Apologies to anyone who works there, but they're probably not watching this video because they're already experts at this stuff. Let's see, what are these JSON Web Tokens? So it's based off of one of these standards. So if you control click here, you'll see some really hard to read plain text stuff. You gotta love these standards organizations. Far be it from them to make readable documentation. All right, that rant's over. So what are these things? They are a self-contained way for securely transmitting information between parties as a JSON object. This information can be verified because it's digitally signed, and we'll go into that. And the signing can be done with an HMAC algorithm or a public-private key pair using RSA or ECDSA. So we'll look at this later. You can remember in that struct I had a public and private key pair, and I had a string. And the string is what is used to sign a JSON Web Token with HMAC, and RSA will show how to create these keys later. So usually these JWTs aren't encrypted, but they can be. I've seen that in some tools. I think Google might be doing that in their OpenID. I'm not 100% sure. It is possible. But what we'll be using is signed tokens. And so these are readable to anyone who has the token. But what they do is they verify the integrity of claims or the JSON properties within it. An encrypted token can hide those claims, but in our case, we will not be encrypting the tokens. When tokens are signed, that means that the signature also verifies that only the party holding the private key is the one who signed it. Our main purpose for using these tokens is for authorization. And as it says, this is the most common scenario. Look at us. We're not out of the ordinary. So once the user is logged in, each subsequent request will include the JWT, allowing the user to access routes, services, and resources that are permitted with that specific token. So we might include some ID that then your service could use to look up and see what privileges that user has. Or sometimes people might include some sort of authorization boolean or role inside of the token itself. And there are various opinions whether you should do that or not. As with all sort of authorization and security things, not a lot of great standard ways to do things out there. People like to argue vehemently. So we talked about all the signature and all that jazz, but let's see how the token looks so that then you can understand what the signature is doing. The JWT consists of three parts: a header represented by XXX here, a payload by YYY, and a signature by ZZZZZ. I forgot to do the fifth letter before, very important. So let's look at what these parts are. So usually the header that becomes XXXXX is just some JSON that tells you what algorithm was used. So here they're using that HMAC that was mentioned earlier, and it's identified by HS256. And this is just so libraries can know what method to use to verify a token. Maybe there's a better reason, and I guess you want to have a compact way of identifying what the token is, so you need to include it somewhere. This is then base64 URL encoded, and let's look at what that is. If you go back to the home page here, you can see an example of a JSON Web Token, and you see this header is in red, corresponds to a base64 URL encoded value here. And so that's what a base64 encoded value looks like. And so this is the 5x's that you saw before on the last page. So the second part of the token after the first period are claims. And so claims is kind of a weird word, but they are statements, it says, about the entity, or in our case, the user, and maybe additional data that your server finds useful to identify the user. So there are some registered claims, and these claims tell who issued the JSON Web Token, so that might be my domain name. It gives an expiration time so that the JWT is only valid for so long. A subject might be the user, I think, or their ID, and so forth. I don't know all of these, but there is a list here, again, in boring, awful, unreadable plain text. Then our JWTs might also contain some private claims. And so this might be things like the user's email address, their image URL, but there are some standard names that you can find here. And we'll use some of these. I actually didn't check to use this registry, so maybe I should update that. But as you can see here, you have things like email, website, picture, profile, and so forth. These are also encoded as a base64 URL, and that's what this second purplish fuchsia-y string here is a base64 encoded value of a subject, some sort of ID, a username, and this is a IAT is an expiration given in Unix time. Lastly, you will have a signature. This signature is used to verify the message wasn't changed along the way. So why is it important to make sure it is not changed along the way? So we're back in the debugger on the homepage of jwt.io. So what does it mean that the signature verifies that the content wasn't changed? Recall that in this example on the homepage, we have some base64 encoded values and a signature. This signature depends on the values inside of the payload. So if we just erase a single character, you should see a message saying invalid signature. And you might also see that the signature changes. Well, the signature doesn't change in this case, but it will no longer match the original signature here. This signature does not correspond to a body without Q. So this would fail. So say someone tried to change an admin flag inside of the body and it's set to false and they steal your token and change it to true and then try to do all kinds of damage and access resources they're not authorized to. I mean, you already have a problem. They've stolen your JWT, but they cannot alter it and then get more privileges. So now the question is, how the crap are we going to use this in our application? Remember that we have defined a token pair, which our new pair from user method returns. So why is this? We are building right now this account application in yellow. I'm going to zoom out a little. It's a little pixelated. And what this does is two main things. It manages authentication and creation of authorization tokens, what this diagram shows, and then it will allow a user to update a few details about themselves, like email address or profile picture. A user can sign into our application or authenticate by entering a valid email and password, or when signing up. When that occurs, the user is sent a token pair in JSON form, and that token pair will include an ID token as a string and a refresh token. These ID tokens will be short-lived. As we see here, they're valid for 15 minutes. We're going to sign these ID tokens using RSA signing with a private key, and these RSA tokens are verified or checked with a public key, and we'll see why that's important shortly. If this short-lived ID token is expired, they can reach out to a different URL or endpoint and say, hey, I have a refresh token. If the refresh token is valid, then they're sent a new ID token. This refresh token, in our case, will be valid for 3 days, and it will be signed with a secret string using HS256. If the refresh token is valid, they will then again be sent an ID and refresh token. Often you might just be sent a new ID token, but we're going to do something called revolving refresh tokens, where the refresh token will also be updated along with the ID token and will invalidate the old refresh token. So why these two tokens again? Let's scroll down. The ID token will be used by passing it as a header and sending requests to various applications or microservices inside of our organization or domain. In this case, we're going to build a word mem app or a memorizer app. I changed the name, but I forgot I changed the name. And these applications verify the ID token with the public RSA key. So we'll create a key pair of a private and public key, and we'll send the public key to all of these applications. Now, we could also use a secret string and send it to these applications, but again, this project was for my selfish learning experience, so you have to deal with my decision. If these tokens can be verified, or if they're valid, the applications can choose to grant access to particular services or features, and in this case, that would be to create a list of words or things to memorize. When the user sends their request, they make sure to provide this ID token string inside of the auth header, and it's tradition to put bearer. I almost kind of want to remove that. I don't get why you have to include bearer. Maybe there's some other authorization out there. Let me know. And then you could send some body. This body might be a word to update, a URL of the word, etc. We'll soon see the differences in the content or payload of the ID token and refreshToken, but our ID token will basically store the user information in the model.user that we created, the domain level model, and the refreshToken will basically just contain a special ID so that it can be recognized and invalidated. So back in VS Code, I have the token service file open. We do not yet have an implementation, which is great. We get a warning here that our new pair from user needs to be implemented, and I think I have some type errors because it is implemented here. Let's see what our errors are. Yes, we are missing the context. Just like we did for creating passwords, I want to create some utility functions for creating and verifying tokens. So inside of service, let's add a new file called tokens.go. For working with these tokens, we're going to use what I think is the most popular library for JWTs in Go called JWT-Go. It's popular, and I think they're going to update to a version 3 I see in the README. Make sure to go get this package or include it in your imports, and then our Docker will go get it for you when you run the application. You probably need to go get it locally too, so it will work with the test. So just run go get this string. Inside of this utility function, we're going to do the following. We're going to define the structure of the payload portion of the JWT with this type ID token custom claims. We'll do the same thing for refresh tokens. If you recall, there are some predefined claims that we can use with JWTs, and that's what this JWT standard claims contains. So if we control and click this, you can see there are some basic fields that are standard to JWTs, and that these claims already come with JSON tags here in the struct. We then set an expiry time in seconds actually by taking the Unix time and then adding 60 times 15 seconds for a total of 15 minutes until expiry. We then initialize the claims here or instantiate them with the ID token custom claims, and we add a user to it, so this will contain things like our email and website and image URL. Take note that our user, if we look at it, will this take it to us? If we go to the model user, we see that our password here has a dash in the JSON struct tag, so we want to make sure and test that our password is never sent to the user in a token or by any means whatsoever. That was kind of a side note, but we'll look at that in a test. We then create a token with the JWT library, and we're going to use the signing method rs256 or rsa256, and then pass the claims in. This creates a so-called token, and we want to return a string to the user, so we'll call the method signString with the key. And what is the key? That is this RSA private key that we will pass into this function, and will end up coming from the token service struct. Let's now take a look at the refreshToken. The refreshToken is quite similar to the ID token with a few differences. First of all, you'll notice that we're going to take the current time as a time, not as an int in seconds, and we're going to add 3 days to it. We're also going to create something called a token ID using a version for UUID. We're then going to create refreshToken custom claims. We define these up above, and you notice that we're not adding a user to the token custom claims here, simply a UID, and we're going to end up using this to identify the user in Redis because we want their refresh tokens to be able to expire, so we need to store them in some sort of fast access database, although some would argue you don't need to do that. Inside of the standard claims, you can see that we're going to add an issued at. I don't know why I did that here. Maybe that was for Redis. We're going to also add an expires at, like we did above, and an ID, which is this random UUID. And this will also be used to expire old tokens. Then we're going to return, instead of returning the signed string directly, we're going to return this refreshToken struct, which if I scroll up fast is defined here. And so that contains a signed string, an ID, and an expires in duration. And again, this is just going to make it easier for our service to interact with the token repository, which we've yet to create. We could end up just returning a string and then reparsing that string again, reading that JWT, and reaching out to the token repository. But it's easier to avoid that step just to return this as a plain struct in our application. Now that we have these utility functions for generating tokens based on keys and strings in the case of the refreshToken, where do these come from? So I'm going to use an example from Google Cloud. I'm going to use a technique recommended by Google Cloud, which you can find at this webpage. And this is used for accessing cloud services using an RSA key pair. I'm going to use OpenSSL here. And so I'm just going to copy this algorithm, which creates the first line, creates a private key, and then from that private key, it creates a public key. So I'm going to take this, modify it a little inside of a Makefile. I'm not an expert in Makefiles, but let's add one anyway. So I'm going to add the Makefile at the root of the project directory, which is one directory above the account directory. So I'm going to open this memorizer here, new file, and Makefiles are often with no extension. They just say Makefile like so. So to this Makefile, I'm going to add a variable, the current working directory, which just runs a shell script to get that working directory. And then for the account path, meaning the account application, we're just going to add a /account to that. Then we're basically going to run that OpenSSL commands that we saw before on Google, but we're going to add some paths to it so that it will be saved inside of our account folder. We also add an underscore and then an M variable, which will pass when we call this create key pair command inside of the Makefile. I don't know if I'm using Makefile terminology correctly. There's probably some people who worked on C in the 80s who are pulling out their hair right now. Again, they're probably not watching this video. So then this line will make the public key. So let's go in the terminal and let's run make create key pair, and then we're going to put the environment as test. So we're going to make one that has a suffix of underscore test. And make sure you're in the root folder, not the account folder, because this Makefile is in the root of the project. So if we run that, we should get 2 files here. Now, one thing that's very important is you probably don't want these. Although in the test case, it's probably okay. You might get a warning from GitHub or your online repository storage. But I'm going to add these to gitignore, so make sure you create this yourself. Make sure. But let's anyway add this to gitignore with .pem here and probably a star up front. So let's save that. I'm going to use the little git console here in VS Code and make sure there's no PEM files. Good. So our keys will not be uploaded to GitHub. Let's take a quick look at these PEM files though. So this is what a public key looks like. This is what will get sent to all of your microservices. And then we have our private key, which will only be on our account application for signing these keys. Buenísimo. All right, so you may remember that like 45 minutes ago, we scaffolded out the new pair from user method, and we didn't implement anything. That was because we needed to create these utility methods and go into great detail about JSON Web Tokens. So let's now finally implement this method. All right, so here it is. We create the ID token with that generate ID token function we created, and we pass the private key from the token service struct. We check for errors, and we do something similar with the refreshToken. Now I've added a little to do. The final code will store these refreshTokens by reaching out to a token repository. And that token repository, as we've mentioned, works with Redis. So then we'll just return this token pair, and it has the ID token and a refreshToken's signed string. Notice that we return the .ss. So that is all for the implementation. And let's go ahead and add a basic test for this token service. And I say basic, but of course it's not simple. So let's do that. We'll create a token_service_test.go file. And I'm going to add a whole bunch of code with a single test case, which we'll explain. Be sure to check out the written tutorial or the repository if you need to see this code in more detail. All right, so what the heck are we doing here? First, remember that we created, it's not in our Git, but in the root folder, we have these public and private keys. I want to read those in as a file using readFile, which returns what type? A byte slice. Great. And then we'll do the same for the public key here. Then the JWT library provides a nice parse private key from a file or a byte slice, and that returns us an RSA.private key, and this will return us an RSA.public key. So we'll have a private and public key of the correct type, and then the secret, we can make anything. Eventually, we'll probably want to store these in environment variables. For example, if we set up a script to run all our tests, we could inject these test environment variables, or for our dev environment or production. Maybe we'll get around to that. We'll see. We'll instantiate a token service with these keys and secret, and create a sort of dummy or mock user here with a random ID, and simply for now an email and password. We won't add all of the properties. Let's run a test to make sure that this returns a token pair with proper values. So we'll create a context, just a dummy context, so that we can call our new pair from user here. We'll reach out and get the token pair. Then we want to assert that no errors returned from this call. And then next, we'll create a string S, and we're going to use the testify assert isType method to make sure that this token pair is a string as expected. Next, we want to check the actual body of the token. So I'll just reuse the JWT parse with claims method, which takes the ID token or whatever token you want to parse, and then the type you want to cast it to, which we define up above, and then a function. This is kind of a funny way that the library does this. I'm sure there's a good reason, but we need to return inside of this sort of anonymous function the public key. And what that will do is then get our ID token claims as a Golang struct. We'll assert there's no error in this parsing step. Next, we want to make sure the claims of the ID token are correct so that the UID, email, name, etc., all match what we're actually going to get. So we add these into slices, and we can just check to make sure the elements in these slices match by using the elements match method of Testify's assert library. We also want to assert that the user password is empty. Now recall that when we created the mock user in the setup here, we added a password, Blargity McBlargface. Very, very good password. And so we want to make sure that's empty as a test that the tokens do not send a password. We're then going to take the ID token's standard expires at claims, and we're going to get this into the time format. So we use the .unix method to convert int seconds, which the token stored in seconds, into the time library's time type. So then we check that this time here is within a reasonable amount of 15 minutes. So we'll create 15 minutes by saying time and then add 15 minutes. And we can use the assert within duration method to check to make sure that the actual expires at token is within about 5 seconds of 15 minutes. There may be a better way to test these kind of time things. I said, okay, 5 seconds is a reasonable tolerance for me, and these tests have to execute. We do a similar thing for a refresh token. We check that the refresh token is a string, and we check that its UID property is as expected. And finally, we check the expiry is within 5 seconds of 3 days. So let's run this test by cding into our account because we're at the root folder. And let's run go test verbose flag and the service layer. So everything is okay and it passed. We could do something like change that the time is within maybe 1 millisecond. So that means our test probably won't finish before the millisecond happens. So let's change that. And hopefully see that it fails. And we do get a fail saying that the max difference allowed is 1 millisecond, but there was a difference of 237 milliseconds. So let's change this back to 5 seconds. Let's rerun the test one more time. And it's passed. Excellent. If you're ahead of the game and worried about how to deal with these JWTs in client-side applications, go ahead and check the description for a rant on storage of tokens or sessions in clients. Next time, we're going to create and run our Postgres database and also create a user's table with columns corresponding to the user model. After we successfully migrate a table, we'll initialize a database connection and perform dependency injection. After that, there are a few errors I've made in the code, so we'll probably have a hopefully short cleanup video. See you next time. Hasta pronto.